Simon. I'll be talking about Tierra mainly, and some work we've been doing looking at things that we might call biases within the implementation of Tierra and the relationship between those biases and parasitism. So the motivation for doing this is, in ALife, of course, we want to make life as it could be, and some of us want to do it in software, some of us want to do it in real chemistry, etc., etc. But I'm often led to wonder when I'm looking at conferences and things, is there too much starting again from scratch, people building their own systems? I'm guilty of this myself. I was part of the team that developed the string mold system, but I wonder if we can do better by developing existing systems, such as Tierra, Vida, etc., one that we've just seen now. And if we think that we can do better by developing those systems, how might we do it? So in this paper we look at improving the design of Tierra. Now this word improving is a little bit of a weighted term. Cleaning might be a better way of looking at it. I'm going to talk about several changes intended to improve the influence of the intrinsic fitness on the evolution of the system. And this is basically the ability of the Tierran individuals to self-replicate based on their own properties in their own genome, rather than properties that are existing in the software environment. I'm going to call this process debiasing, but I've got a few things to say about that in a moment. In order to measure the differences in the two systems, I'm going to use an evolutionary activity measure that we developed a couple of years ago to allow us to compare what's going on in systems like this at a sort of high level. So first we need to sort of have an idea of what Tierra is. Again, we're interested in what the models of systems are, how models work. And without having what you might call a domain model of the system, you can't really say what a bias might be in that system because you don't really know how the design is working. So a quick sort of tour of Tierra. The main structures in Tierra are illustrated in the central column. The environment consists of a bunch of memory, usually 60,000 bytes, which is referred to as the soup, referring to the Mille-Urey experiment about primeval soup. And within that memory, little regions of memory are partitioned off into what are called creatures, individuals. Okay? And the individual is made up of a program, which I'll come to later, but then a bunch of other computational apparatus. It takes CPU time from a queue called the slicer. It has pointers, which tells it where it is in the program, and it has a stack, which allows it to store bunches of information. The individual also has a genome, which is basically the program that executes when the CPU gives it processing time. And the program is made up of a series of opcodes. These are tiny little computational instructions. And one of the key breakthroughs of Tierra was how this system worked and how the opcodes were designed so that you could never crash the universe. The individual also has registers where it can store values, but it has a finite life. When the memory gets full and a new creature is born, another creature is selected to die, and that's done by virtue of its position on this thing called a Reaper queue. So basically, when you're born, you're placed at the bottom of the Reaper queue. As other creatures die, you move up the Reaper queue, and eventually you're old enough to be selected for death. I'll talk a little bit more about that as we go through. The key innovations of Tierra were that you could observe this optimization of the self-replication process. And it was a really neat piece of work at the time. We saw the emergence of these complex patterns of parasitism, which I shall also talk about as we go through. And all of this worked in an uncrashable execution environment, so the universe didn't just suddenly fall over no matter what the instructions did. That's all really, really important. This quote from Joseph Heller about the book Catch-22 I think is quite appropriate here, because I don't want to give you the impression that I don't think Tierra is a very good system. I think it's an amazing piece of work that was done 20 years ago. I think there's still a lot that we can learn from it. But Tierra is an emulation of life, not a simulation. So you're not saying it's an observed process in real biology that we are trying to simulate and copy. It takes ideas from all over biology, and interestingly, a lot of different scales that I think is perhaps an issue when you're trying to understand what's going on in your system. Okay? But the biases that we've identified influence the intrinsic fitness of the creatures in the system. And this is basically their ability to self-reproduce should be its own fitness in its own way. It shouldn't be anything else. So what we're calling biases are things that influence that ability to self-replicate. and there are 4 of them. The first one is what I'm calling reaper bias, and this is to do with the position of the individual in the reaper queue, which gives its chance of death, basically. And what you get there is when certain functions are executed within the individual, the position of the individual in the reaper queue is changed. So in a way you get a double hit for correct behaviour. But that kind of means that you are saddled with the behaviour that was in the mind of Tom Ray, who designed the system. And that kind of limits potentially emergent properties that could happen, I would argue. In addition, there's substitution bias. When mutation happens, an opcode is not replaced with any other opcode. There's actually a small list. It's done with a bit flip lookup thing. And that means that you've got to have some sort of relatedness between the opcodes in the system. And again, you're in the mind of the designer of the system, and you're not allowing more sort of wide-ranging mutations to happen. Now, in the string model system we've developed, we do things like this, and we're just asking this question: is limiting the variability in the system in this way influencing what we see coming out the other side? 2 other things we've observed: length bias. The mutation rate in Tierra is dependent upon the average length of the genomes of the population at any particular time. And that means that the mutation rate can change, and that, I think, would bias the system towards shorter individuals, because shorter individuals are less likely to have a mutation. And finally, the zero address bias. This was identified by Barry McMullen's group in Dublin, who were working on Tierra a few years ago. There isn't time to go into details, but basically the individual that exists at address 0 has some benefit from that based on the way some of the opcodes work. And I'm going to call that an undocumented niche. There's a special benefit in being at that system. I just want to say again, without the domain model, we can't be clear what the model should be doing. I'm just saying these perhaps influence the system in ways that we might not want to see if we want to study ALife generally, rather than the Tierra system as it exists. So as I say, we're using this evolutionary activity measure as our top-level comparison of the system in the experiments I'm about to describe. We first presented this in Michigan in 2012. It's developed from earlier measures of evolutionary activity. There's 2 key properties, I think. Firstly, it doesn't require a shadow model in the system. It basically looks at intrinsic and extrinsic fitness the same. And essentially, it looks for these ramps that happen in population dynamics when you get this evolutionary change from one species to another. So here the dominant species goes extinct, and here a new species emerges. These are the actual scores per time step, activity per time step, and you can see most of the activity happens during this switch, but where you get the emergence of subpopulations, you do get a little bit of score. Okay? And what you do to get a top-level number that says how well an individual simulation is run is basically you sum these peaks along, which is what this little equation here tells you. More details about that in the paper, should you want them. And we've used this system to look at Tierra and at stringmol. Any system where you can get the number of species and the populations of each of the species throughout time, you can apply this measure to. And I think it's pretty useful for software systems. So, on to the experiments. We used high-performance computing facility here at York to run 100 simulations of Tierra 6.2 versus our debiased version. Each simulation ran 10 billion instructions, so these were very long simulations, created a heck of a lot of data that we had to deal with. To get the top-level comparison, to try and weed through those 100 simulations of each system to see where the interesting systems were, we used the evolutionary activity measure to give us a distribution of activity. Okay? And then we looked in detail at the minimum, median, and maximum performing runs with those systems. So the first thing I want to show you is the QNN activity values for all 200 trials. And we looked at them in 2 ways. Firstly, we looked at every species that Tierra produced, which is this graph here to the left. And secondly, we looked at the dominant species, the species whose population at any time rose above 50. The total population in the soup of Tierra is in the order of a couple of hundred, so this means that there are dominant species going on. And I think due to the noise of the system, the amount of species that are produced, etc., I think this is legitimate, as you'll see. So what we found was that if we looked at all of the species, Tierra 6.02 had this sort of trimodal distribution of performance, whereas debiased Tierra just sat there flat at the bottom. But what was interesting was that if we looked at the dominant species, we get this interesting bulge of activity, and these particular trials here, where the activity was very high. And that allowed us to go in quickly to zoom in on the runs where the interesting events were happening and kind of try and tease out what was going on. So we didn't really do any low-level stuff, but I'll talk about that as we go through. So I've only really got time to talk about the maximum scoring runs in each trial. Okay? And in these plots, the red lines and bars indicate the dominant species, whereas the black or grey lines indicate the data for all species. So row A basically shows you the distribution of genome lengths. Wherever there's a little dot, it means that a genome of a particular length existed in the simulation at that time. Okay? And then the bottom row basically shows the number of species that were existing at any particular time. Okay? I want to point out a couple of things to you now. Firstly, for all species, the species tended to be shorter. Okay? And where you have a soup of a fixed size, that means that you get more individuals in the species. Whereas in debiased Tierra, we've got much longer individuals, and that basically meant that there were fewer of them in the soup. Another thing I want to point out to you is the bottom end of this graph. Okay, it's very hard to prove, but Tom Ray makes a claim that the shortest reproducing individual in Tierra had a genome length of around about 22. But parasites, smaller individuals, can exist with a genome length of around about 12, etc., etc. And what you see here is that you get a lot of dominant species that are of the length of parasites. And we've checked a few by eye, and they are indeed parasites. Okay. Whereas in debiased Tierra, remember this is the most active system that we have to look at. In debiased Tierra, there are no parasites persisting for any length of time. Okay. And I also want to point out that there are many fewer dominant species in debiased Tierra, whereas you get much more variability in terms of the species that exist that are dominant in that system. Now, my claim that in the title of the talk that environmental bias forces parasitism is based basically on the absence of red lines in this area. That means that although parasites emerge, they are not forced upon the system, and the system can recover from them and exist quite happily. Whereas here you've got this much more sort of parasitic situation going on where parasites are there in high numbers and interacting with longer individuals in the system. Am I doing for time?
We still have 7 minutes.
Oh, okay, great. Okay. So the key results, I think, from this study are that in a debiased system, you get longer genomes and the population size is smaller. The number of dominant species is fewer. The species for QNN score for the debiased system is diminished. There's not so much evolutionary activity going on when you remove these things, when you're considering all species. But if you look only at the dominant species in the system, you get this raised area of QNN score. Okay? So those are the core results. Hopefully none of that is high.
How do the dots in the all species map to the dots in the other group? Like, are the very species-rich simulations in a specific area in the other graph?
Oh, okay. So this red dot here is all of the data, is the evolution, some of the evolutionary activity for all of the data. I'm trying to go back, I'm failing. So this run, all of the data in this run is compressed into that one number there. So that's that run there. Sorry, I should have said that before.
Okay, I didn't explain myself properly. In the all species measurement,
Yeah.
I guess you're using the same simulations as...
Oh, I see. Yes, yeah. I understand now. Yeah. These are the same simulations. I haven't looked into that, and perhaps I should. Yeah, that's a good point. So a dot here corresponds to that dot here, but I can't tell you which one of those it is, I'm afraid.
It would be interesting.
Yeah, it would. Yeah, good point. Okay, so those are the key observations. I'm going to give you my interpretation of those observations now. I want to argue that debiased Tierra is a level playing field for Tierran genomes. It actually means that you will reproduce by virtue of the ability of your genome to help you to reproduce, rather than these other features within the system. Okay. The number of species is less, partly because of the reduced influence of parasites, because the reproduce doesn't reward their good behaviour, so you get this constancy of the species, but it is also, of course, because of the limited size of the soup. One thing I've not been able to point out sort of with graphs is that fault tolerance is higher. We actually see fewer runs terminate early in the debiased version of Tierra, because there's less volatility due to the effects of the parasites on the system. Okay. Evolutionary activity is higher for the dominant species because you're getting recovery from and resistance to parasitism, which allows the reproduction of the self-replicate, the evolution of the self-replicators to actually become prominent in the system, I think. So the conclusion for the ecologists in the audience might be that you're getting a more K-selected optimum after debiasing the system, which I think is kind of an interesting property of what we've got here. So I started this talk by asking, can we do better by developing existing systems? And I think we can, okay? And what I've tried to do here is remove some of what you might call the complicatedness from Tierra to get a cleaner implementation of the thing that we're actually interested in, which is the emergence of complex self-reproducing individuals in the system. Okay? So further work. What we did here was we removed all the biases that we could in the time available and looked at the difference. But what we really should do, of course, to do the science well, is to explore each bias individually. Okay? And we want to apply this to a range of Tierra configurations. We've only looked at the off-the-shelf Tierra test critter. And we need more and better measures of evolutionary activity. Although this is evolutionary activity measure represented here has been useful in this environment, I think we need a range of them to really understand what's going on in these systems. I just want to advertise source code for this. I've asked for permission from Tom Ray and got it to store on GitHub my version of Tierra that uses that, and it also incorporates Declan Bow, Barry McMullen's students' changes. That's from Tierra. If you're only interested in evolutionary activity measure, that's there, that's QNN. So please do go and have a look at that if you like. I'd be really keen to see that being used. Final word, this work was carried out on the Evo project here at the University of York with Susan Stepney, my PI. Thank you very much for listening.